Hi, my name is Omar Gadala. I'm the RDT Product Manager for Parkson Corporation. I'm here today to give you a presentation on the Thickener rotary drum thickener. Just to give you a basic overview of how a thickener in general works, and specifically a rotary drum thickener. This diagram here shows what incoming sludge typically looks like coming out of a waste-activated sludge system. We typically see anywhere from 0.5 to 1.5% coming in, and what we do is add a polymer water solution to that sludge, which what that will do is gets the sludge to flocculate together. It gets it to form solid groupings of particles, that way that they can get mechanically separated through our rotating drum. Once the polymer and water solution is added, it's put into a flock tank, which is really just a tank to add some resonance time to allow the reactions to occur. It allows the polymer and the solids to kind of group together into what we call flock. And once that's done, it goes into a rotating drum, a horizontal rotating drum, which just separates out the filtrate and the water. And as you can see here, we have some pictures of what the filtrate, the clean water coming through the drum looks like versus the thickened sludge, which comes out the end. To step back a little bit, why are we thickening sludge in the first place? And the reason is most of sludge, the very high percentage of it, up to 98, 99%, is water. So anything you're going to do downstream in a process, you're going to have to do it with the water in addition to the sludge. And that's not very good economically or environmentally, especially if you're transporting it off-site. Now you're going to be shipping 99% of your volume is going to be paying to ship water, which is going to have trucking costs and fuel costs, etc. So if we can remove some of that water through this process and only remove what you actually want to, which is the sludge, it saves a lot of money and it helps environmental matters as well. And even if they're not doing transshipment, if, for example, if you're going into a digester after your waste-activated sludge system, it increases the digester capacity by removing space and makes it work a lot better if you have more solids and less water involved. So there are a number of different technologies that can thicken sludge, that can remove some of the water from the sludge in a thickening process. So why do you want to use an RDT as opposed to, say, a gravity belt thickener or something along those lines? The number one reason is RDTs are fully enclosed, so they lend themselves greatly to odor control. They also have a much smaller footprint and are much neater because of their enclosures. Again, because they're not open to the top and open to the environment, they can be installed inside and outside. They're also extremely easy to operate. They have very few controls. And the Thickener specifically, the Thickener RDT, has very low polymer usage. So why is the Thickener RDT better than any of the other RDTs on the market? Number one is we have the industry-leading performance. We can get up to 8% dry solids on the dewatered cake, and we can also get over 98% recovery of solids, which means you're not retreating the same solids over and over again and dosing with polymer the same solids again and again. Experience. There's over 200 RDTs installed at over 150 locations. And they've been out there for 20 years, which is unsurpassed in the marketplace of rotary drum thickeners. Also, there's low operation and maintenance cost. Electrical requirements are very small, and there are large polymer savings costs, specifically with the Parkson Thickener unit. And the units are very robustly constructed. Now, the first thing that makes the RDT, the Thickener RDT, different than others on the market is the tangential inlet and outlet of the flock tank. As I mentioned before, the polymer gets added to the sludge, and then it's important to allow resonance time, but not mixing to occur. The type of bonds that are occurring between the sludge and the polymer that are causing the flock to occur are intermolecular bonds, intermolecular bonds, not intramolecular bonds. So they can break apart very easily. And what you want is a lot of resonance time just to allow that flock to happen, allow those positive and negative bonding to occur to get the solids together without any sort of mixing. So in order to do that, we have a tangential inlet and outlet. So the inlet is actually tangentially fed, and as you can see, it follows the natural flow pattern of that helical motion up through the flock tank. This allows for a lot of resonance time, but it doesn't allow for a lot of turbulence or mixing. Other RDTs on the market do not have this aspect to them. and they actually use perpendicular inlets and outlets on circular tanks. Now, this causes almost a 90-degree turn to occur the moment the sludge enters the tank, and even after the flock sets up, once it leaves, it's again being forced to turn 90 degrees. That shearing removes some of the flock buildup that you've been trying to create in this flock tank. Another thing to keep in mind is that there's a impeller always turning here. So as that flocculated sludge is leaving, it's hitting an impeller, and then it's causing shear, and then you lose your flocculation. Another form that we see out on the market is a square tank with the same inlet and outlet. So as you can imagine, that even gets a much greater mixing occurring, shearing occurring, and therefore less flock set up. When you have less flock set up, you have to add more polymer, and polymer is very expensive. Another thing that makes the ThickTech RDT different than others on the market is the screening material. What you want when you're screening, you're removing liquids from solids. You want a lot of overall open area with the smallest individual opening size. The smaller opening sizes keeps the solids in and allows the water to go out. But the more open area, the more of those openings you have, the more water removal you're going to get and the less polymer you have to add. Again, a major cost savings item. So as you can see here, what we typically see on the market, there's 4 general types of screening materials. There's the woven wire mesh, which we use, wedge wire, filter cloth, and perforated plate. Now, just by visually looking at this, you can see the ratio from open to closed areas on the woven wire mesh is significantly higher than any of the others. Now, regardless of the spacing that's allowed in a perforated sheet, how it's punched, or the wedge wire, how it's spaced, fundamentally what you're dealing with here is the open to closed area is much larger, as in there's more closed area than open in any of these other materials. And that's why we use the least polymer. That's why it works so well. Another thing that is occurring, once you have these solids and liquids inside the drum, you want to get the liquids to separate from the solids. Now that separation only occurs at the very surface where the sludge and the water is hitting the screening material. So it's very important to induce rolling, to induce flipping, to turn and move the sludge around. Now within the Parkson RDT, the ThickTech, you actually have a bunch of different attributes within the drum that allow this to occur. Number one, you've got roll bars, which are bars that go along the entire inside of the drum that actually cause the sludge to flip over. This takes the sludge that's on the top and makes sure it gets on the bottom so that the sludge is always seeing that surface, and there's new sludge and water always seeing that surface where this reaction is occurring. The second is we've got 4 distinct dewatering zones separated by split augers. Now what these split augers are is it's a flight that actually goes around the entire length of the circumference of the drum. Therefore, the sludge is actually held in each one of these components and it has to overflow to the next section. It's not allowed to just hydraulically slide through. In addition to that, we have flights and we also have detention ports. The detention ports are there in the split augers, so if you do want the sludge to go through the drum faster, you can open them. It allows that operational ability to change. Now, to take a comparison to a perforated sheet drum, there are no internal components. The sludge is allowed to just hydraulically slide through, and it does not ever get flipped or rolled or turned. It doesn't get detained in the drum. Nothing happens to it. It just merely slides through the perforated sheet. And to show a wedge wire drum, which is another one of the leading RDT manufacturers, the only internal component they have are just small flights. Now, without the split augers, this is actually pushing the sludge through faster, defeating the purpose, as opposed to detaining it and then flipping it over. Now, to take these two things, the screening material and the internal components together, you can see that while the sludge is in the Parkson drum, not only is it being held, is it being rolled, is it being flipped, all the new sludge and water is constantly being exposed to that screening material where this thickening is occurring, where this water removal is occurring. It's occurring through a much larger open area. Combine that with something like the perforated drum, and you can see that the water and the sludge will very easily slide right over without any separation. There's nothing actually physically getting that water to separate. There's also nothing that's getting new sludge and water to the surface, which the surface itself doesn't have as much open area. You combine all these things, and the same with the wedge wire as well, these drums will have water removal. They will thicken sludge, but we will take a lot of polymer usage. The dosage will have to be extremely high for these to get to the same levels that you're going to see with the woven wire mesh drum. So why is this so important? Polymer use costs a lot more than the drum itself. Now, in the industry, we all know that polymer is expensive. How expensive is it? That's the thing we really need to think about, because it's something that's taken into account when picking a drum out, but it's not something that's a make or break decision maker. We sort of take polymers the same way that we take gasoline prices for a car. We all know fuel efficiency is important, but you rarely see anybody who picks a car based purely on fuel efficiency. Well, what I did is I took the look at how much polymer costs versus the cost of the drum and how much gasoline costs to a cost of a car. So how could we make those a 1-to-1 ratio? Well, we would have to have gasoline at $119 a gallon. So now think about this. If you're purchasing a car for $119 a gallon, how important is fuel efficiency now? Extremely important. If a car costs 30% more but can save you half on gas at $119 a gallon, you really don't even have to do the math. We all know that that expenditure is well worth it. It's typically paid off within the first year. And that's the same economic model we're dealing with RDTs versus polymer cost. The only difference is, instead of having to go to the go-kart, as in this diagram, the higher performing RDTs are actually the better RDTs. They're the nicer ones. The ones with the more bells and whistles, the ones that are better designed, better put together, also have the lower polymer usage. So you're not having to give up going to a go-kart versus a Hummer, as in the example, to save the money on gasoline, or in this case, polymer. So let's take a look at how much polymer actually costs on the life cycle of a 400 gallon per minute drum. Based on a 400 gallon per minute typical operation of 8 hours a day, 7 days a week with 1% sludge, you're looking at a capital cost on average through the industry of about $180,000. This is all the drums that we've seen that are out there now. At 20 pounds per dry ton, which is about your average polymer usage, much higher than what we see in the Parkson RDT, you're looking at $320 a day on polymer and $116,000 a year. So your first year, you're approaching your capital cost already. And over a 15-year life cycle, you're looking at $1.43 million in polymer cost versus a capital expenditure of $180,000. Now, if you compare these two, you can see where that differentiator is, where capital cost versus operating cost. If your operating cost is half for one RDT to another, it saves you many times the actual capital expenditure of the entire piece of equipment. So to give you a more detailed example of this, looking at 1,000 gallons per minute, which is a more realistic scale that you will see in the industry, same type of operation, same discount rate, you can see how much the cost over 15 years changes with the differences in polymer dose. We've seen polymer dose anywhere from 5 to an excess of 35 pounds per dry ton. So for this specific example, the cost of polymer can range from just over $500,000 over a 15-year life cycle up to $4.5 million. This is extremely important. This is where you need to, this is where the money is going to go in these type of projects. So this is why the higher performing RDT is so vitally important, which is why all the features that I spoke to you earlier about make such a big difference and why they're so well worth it in the long run. Another thing I want to bring up is capture rate. The Parkson RDT offers a 98% or greater capture rate. What we see on the market other than that is anywhere from 80 to 90%. So much like the tortoise and the hare are showing here, if you were running a race and taking 1 to 2 steps back for every 10 steps forward, you're never going to win the race. It's a very inefficient way to run any sort of process. So what you're doing here, in addition to that, is you're retreating those solids. So if you're getting an 80% capture, 20% of your solids are going right back into your system to come out through the RDT again, to get dosed again, to go back out and go right back out into the system again. So you're dosing sludge that you're not actually removing from your system. How much does this cost? Well, for 90% versus a 98%, you're looking at about over $100,000 over a life cycle cost. It's $100,000 of money that you're spending on polymer that you're never actually getting out of the system. For 80 to 98% comparison, you're looking at over $250,000. So over the 15 years, first 15 years you own this piece of equipment, you're looking at spending $250,000 on polymer on dosing solids that you never remove. They go right back to your system again. Another thing to keep in mind is as those solids are going back to your system, you're losing capacity of that treatment system. You're losing the effectiveness of that treatment system. So you have other things like aeration, labor, your overall system size, electrical requirements, and then there's just a general waste of it. If you're looking at a situation where you're going with a 90% capture rate versus a 98% capture rate on a 400 GPM system, the amount of sludge you're not treating, the amount of sludge that's going through your system just to go right back and treat it, could fill the hull of the Titanic 2.4 times. And that's a pretty small system. So think about that. That's how much sludge is going to be get retreated again and again and again simply from a capture rate difference of 90 to 98%. So although it doesn't seem like a lot on paper, it's a very critical difference. Another thing that we'd like to show is that a couple years ago, the Parkson RDT went head-to-head against a wedge wire RDT. So all these things that I'm talking about today with regard to screening, opening size, and internal components, what does that actually show in real life? Well, in this case, a municipality hired an outside engineer to run our unit against a wedge wire unit. And here are the results. For both units to acquire 6.6% solids, the Parkson unit required 9 pounds per dry ton of polymer. The wedge wire screen took 21 pounds per dry ton. So what does that equate to for a 400 gallon per minute unit? Overall, it's a savings of $860,000. The capital cost difference on the two was closer to around $40,000. So as you can see, the cost difference is paid for over and over and over again, and typically within the first year. Another thing I'd like to bring up is the craftsmanship. These RDTs are extremely well made. In addition to all the other design components, there's a lot of care taken into these, and these are very robust, very well put together pieces of equipment meant to last for a long time. So just to review the fundamentals of the ThickTech RDT, we're looking at anywhere between 25 to 400 gallons per minute per unit. We offer units that range 25, 50, 100, 150, 200, 300, and 400 GPM units. So you can get any sort of combination or smaller size capacity that's necessary. The inlet flow we typically see that would offer the peak performance is between 0.5 and 1% sludge. Our outlets solids typically come from 5 to 8% solids. And as I mentioned in the slide before, the 0.5 to an 8% solid is almost a 14-fold reduction in volume. And the typical polymer usage that we see is 5 to 10 pounds per dry ton. Now, as I mentioned before, industry-wide, you're looking anywhere up to 35 pounds per dry ton plus, and we've seen that this is a very high cost item. And finally, the solids capture, the capture efficiency of over 98%. Another thing that we'd like to bring up is the Parkson advantage. What the company as a whole has an advantage. We have over 50 years in the industry with over 25,000 installations worldwide. As I mentioned before, 200 ThickTech installations have been installed over the last 20 years. And we also have a pilot unit that can be taken to prove the effectiveness of the ThickTech unit versus other units, or just prove on new applications and that sort of thing. And finally, lab testing. This is another critical component of setting up an RDT, is picking the right polymer. Different polymers react differently to different sludges. We've been picking polymers for 20 years. So we know exactly which polymers to pick, and this can be another huge cost savings item. So finally, in conclusion, why we're thickening sludge to begin with is to remove water from a system that doesn't need to be there. You don't need to transport water, you don't need to digest water, you don't need to use that water in anything else, and sludge is mostly water. So it makes very good sense to remove that water as much as possible before you move on to your next step. The second reason why we would use an RDT over other thickening methods mostly is that it's fully enclosed, it's clean, it's easy to operate, and it has odor control capabilities. And finally, why we want to use the ThickTech. Industry-leading performance, superior design and quality, and finally cost savings. Very high cost savings over any of the competition through low polymer usage. And now I'd like to open it up to any questions.
What is the payback of a rotary drum thickener versus off-site disposal?
Obviously, that question depends on how much the municipality is paying for disposal of their sludge. What we have seen, especially with gas prices the way they are, if you're trucking it off of site, the capital expenditure of an RDT, and that's not just the ThickTech RDT, but also the building enclosure controls, electrical, everything that goes along with it can easily be paid off within a couple years. The RDT itself is typically paid off within the first year, but again, that's very highly dependent on how much gas is, how much trucking cost is, and how much the disposal is. For example, if it's going to land application, the main cost is a trucking cost. Now, even with those, removing that water and reducing the number of truckloads can easily pay for a project within a couple years. These things are typically done on a case-by-case basis, but it's a pretty easy calculation to do, and I'd be more than happy to help evaluate that for any customers that would want to look into it.
A centrifuge is also used for sludge thickening. How does a RDT compare to that kind of equipment?
Using a centrifuge for a dewatering application is typically a really good use for that piece of equipment, getting it up to close to 20% solids, for example. However, using a centrifuge for a thickening application tends to not be as beneficial in a cost sense. If the centrifuge can actually thicken sludge without the use of polymer, then yes, sometimes it does make sense, depending on what your electrical requirements are going to be. However, the moment that polymer is used in a centrifuge for thickening, which we typically see, then all of a sudden it sort of goes off the cost-benefit curve and doesn't become as good of a viable solution. And you're better off sticking with more traditional thickening processes.